This video is for lesson 1-3, which is measuring segments. So during this lesson, at the end, you should be able to find and compare different segment lengths. So we're going to start with this little diagram here and this situation. So suppose you were freshwater fishing and you're on a trip and you catch this fish here. And the law says that you must release a fish that's between 15 and 19 inches long. If it's longer than 19 inches, you can keep it. So you need to measure the fish, but if you take a look, the front of this ruler is like worn out. So you have to figure out, can you keep your fish? And then explain how you found your answer. So first thing is, it's hard right now because it looks like I can tell that the tail of the fish right here is at approximately what appears to be like 16 inches. So I kind of have to figure out, well, can I keep this fish? So if it was in fact 16 inches, I wouldn't be able to keep the fish, right? I would have to throw it back. And actually, it says 16 inches right here, but also over here, I have to kind of guesstimate. This is probably maybe around like 4 inches. So the difference, like how long this fish is, well, it's already less than 16 inches. So no, I can't keep this fish. So I'm going to answer my question. No, I can't. And how do I figure it out? Well, the fish's nose is not at the end, right? And I estimated approximately, it's between the 16 and the 4, so it's about 12 inches long. So it's approximately starting at 4 inches and ends at 16. So clearly this fish is too short. Let me make this a little smaller. And there we have it. Okay, so how does this tie into what we're going to do in today's lesson? So basically what we do is typically we use a ruler and we can use the ruler to measure different lengths. So think about it in terms of every point on a line is really paired with some sort of number. We call that number a real number. So on a ruler, each little tick mark associates with some sort of number. Now, the real number that corresponds to a point is called the coordinate of that point. So on the ruler here, like this would be 17 inches. So the point corresponds to this length of 17. The 17 is the coordinate of that point. So think about this, right? I have A and B. They're 2 points. They coordinate with the value at B and the value at A. So how could you find the distance between points A and B, here to here? And sometimes we think if it's on a ruler, perhaps we think to like maybe count tick marks between 2 points, right? So sometimes you kind of count like, okay, so count like the tick marks between the 2 points. That could be one thing that maybe you did in the past. But also you can find the difference between the 2 points. Go here. And when we're talking about difference, we're really talking about subtracting. Okay. Now, one thing that's important to talk about when we're dealing with distance, in terms of distance with measuring things, we never suggest that distance is negative. So put it this way. If you dig a hole, you're digging down into the ground. Do you say that your hole is negative 3 feet deep? No, right? Your hole is just 3 feet deep. So something that's really important with distance, especially, is that it cannot be negative. So we in math do something called an absolute value. So even if we get a negative number, we take the absolute value of that number, and now it's positive. So the absolute value of any negative value is automatically positive. If we take the absolute value of a positive number, it's still positive. So distance cannot be negative. So take a look down here at what we're talking about. So here's point A and here's point B. Here's the value, the coordinate of A, and here's the coordinate of B, the value. So we can find the distance between B and A, and we take the absolute value. So these little bars represent the absolute value. And when you take the absolute value, you essentially turn the value positive. After you subtract, say, A and B, if you get a negative number, you take the absolute value, and now it is positive. Okay, so let's take a look at maybe how we're going to actually start to do this. So let's try this one right here. Next page. It says measuring the length of a segment. Let's try it. So what is ST? So remember, ST, I need to then take the absolute value. So I'm going to actually subtract. Well, let's figure out. S has the coordinate of -4. T has the coordinate of 8. Now, using what we saw here, we can subtract A and B, take the absolute value, and that's the length of AB. So we're going to do that. We're going to subtract -4 minus 8, but we need to take the absolute value. So just a little bar here and a little bar here. Okay, so the first thing that we're going to do is we're going to put this into our calculator exactly how we see it. So -4 minus 8. Well, if I'm doing -4 minus 8, that's a -12, right? And now I need to take the absolute value of -12. So that means I just essentially say, okay, well, the absolute value of -12 is +12. So equals absolute value of -12 is just 12. So the length of ST is just 12. That's your answer here. That's how you find the length of a segment. Now let's try this. What is UV? Okay, so UV. So let's kind of highlight. Here's U and here's V. So we're dealing with 10 and 14. So we can do 10 minus 14, but make sure we take the absolute value. So the absolute value of 10 minus 14. Okay, so 10 minus 14, again, put that in your calculator. And if we have 10 minus 14, that's a -4. We're going to take the absolute value of -4. And the absolute value of -4 is just 4. Now, here's a little trick. I'm going to let here UV equals 4. Think about this. I have to go from U to V. So I start at 10, and I go from 10 to 12, and then 12 to 14. So think about it. What's the difference between 10 and 12? How do I get from 10 to 12? And let's just say then I would add 2, right? And then I go from 12 to 14. Well, how many do I add? I add another 2. So if I add 2 plus 2, that's a difference of 4, which is the same thing I got here. Now, if I have to go from S to T, I'm going from -2 to -4, right? So then again, if I'm thinking about this, remember distance is never negative. So that's the difference of 2. And then -2 to 0, well, that's still 2. 0 to 2 is 2. 2 to 4 is 2. 4 to 6 is 2. And 8 to 6 is 2. So that's 2, 4, 6, 8, 10, 12. And that same value is here. So there's really 2 ways to do this if you are given a number line, right? You can do the absolute value of the difference of those coordinates, or you can certainly count along your number line. You did that in middle school and perhaps last year in algebra. So both are actually accurate here. So there are other ways. We are going to focus on just forming an absolute value equation or expression, I should say, that we can kind of evaluate. So let's now look for SV. So for SV, if you want, you can pause this and try yourself. So here's S and here's V. Okay, so the absolute value, right? Let's start with our absolute value bars. Give S to V with our absolute value bars. And the difference between S and V is supposed to be -4 minus 14. Remember, you have to make sure that this is a -4 minus 14. It's different if you make it a +4. You can't just turn this positive before you actually put it underneath or in between the absolute value. Okay, so the absolute value now have to actually subtract -4 and 14. -4 minus 14 is -18. Okay, so now take the absolute value of that, which is just 18. Right? Now we know that SV equals 18. That's how we can find the length of a segment. Now let's go down and start talking about what happens when we actually add segments together. And there's this postulate that comes along with it. And here's what the postulate says. If we have 3 points, A, B, and C. So take a look down here and we'll look at these 3 points. A, B, and C. And notice A, B, and C are all on the same line. So if points A, B, and C are on the same line, they're called collinear. So if A, B, and C are collinear, okay, and B is between, well, B is between A and C. So let's put here A and C. Then what's true? Okay, so A, B, and C, collinear. B is between A and C. So let's think how we could take these segments. So remember, segments are formed by 2 endpoints, and how we can add them together to get a greater segment. So I think you guys would agree. If I take this segment from A to B, and then I add this segment from B to C, I get the entire length from A to C. So we can fill in this statement over here. We can actually say AB plus EC equals AC. So essentially the 2 smaller parts add to give us the entire length. So AB, the segment, plus BC gives us AC. And that's known as the segment addition postulate. So now let's see if we can use this idea down here. And let's take a look at what we have. So we know that EG is 59. We have to find EF and FG. Okay, so first is EG is 59. I like to kind of show that by doing a little bracket from E to G. And then I'm going to actually write in 59. Okay, so now this is what we know. EG is 59. EF is represented by an expression, and FG is represented by an expression. We need to figure out what is EF and what is FG. I'm going to somehow use the segment addition postulate up here. Okay, so I have this and this. These are my 2 parts, right? So in my mind, I'm thinking, all right, well, EF plus FG. If I add from here to here and here to here, it has to equal the entire length from here to here, which is EG, right? All right, and so now what do I know? Well, I know that EF is represented by 8x minus 14. I know that FG is represented by this here, which is 4x plus 1. And I was told that EG is 59. So it actually now looks like some substitution can happen, right? EF is 8x minus 14. FG is 4x plus 1. And EG is 59. So now I'm going to substitute. I'm going to put in for EF 8x minus 14 plus FG is 4x plus 1 equals EG, which is 59. That's called substitution right there. So I can substitute in my values or my expressions and now solve this equation. So remember, now I have an equation. In order to solve an equation, I want to draw my line down the middle through my equal sign. And on the left-hand side, I want to combine like terms. So I take a look. Terms that are similar. We have 8x and a positive 4x. So 8x and 4x is 12x. And then we have negative 14 and a positive 1. So negative 14 plus 1 is a negative 13. So minus 13. Okay? Bring down my equal sign. And bring down that it equals 9. Okay, so I want to work to get this by itself. I can't get this by itself yet because this negative 13 is in the way. So how do I get the negative 13 to the other side? Inverse operation. So instead of subtracting 13 to get rid of it, I can add 13. I add 13 over here. This is an equation. It has to stay balanced, so I have to add 13 to the other side. Right? So on opposite sides of the line, I'm doing the same thing. Okay, so now I draw my line. Now I evaluate. Right, negative 12, I'm not doing anything with the negative 12, so I'm going to just bring it on down. I'm sorry, 12x. Negative 13 plus 13, well, that gives me 0, so I kind of don't have to worry about these anymore, right? And now 59 plus 13 gives me 72. Okay, now is x by itself? And no, it has a coefficient of 12. So now to get x by itself, 12 and x are being multiplied, so let's divide by 12. Remember, whatever you do to one side, you have to do to the other. So I have to divide this side by 12, and I must divide this side by 12. So at the end, 12 divided by 12 is just 1, and x then equals 6. Okay. So I now have a value of x. X equals 6. I'm going to bring this over here. So if x equals 6, remember, I need the length of EF and FG. So let's look over here. EF is represented by 8x minus 14. So I'm going to take the 6 and I'm going to substitute it in for x. So really now EF, I can do 8 times 6. Wherever I see x, I'm going to substitute in a 6 minus 14, right? And then here, wherever I see x, which is right here, I have 4 times 6 plus 1, okay? And then EG I don't have to worry about. So 8 times 6 minus 14, which is then equals 48 minus 14. So I have 48 minus 14, which is 34. And then at FG, I have 4 times 6, which is 24. 24 plus 1 is 25. Right? Maybe a little confusing. So you know what? Let me just do this. I think it might be easier to look at it like this. Okay. Now let's do the same thing here. I'm going to fix the formatting a little bit, so maybe it's a little easier to follow along. Right. So at the end, I found EF and EG, right? I know that EF is equal to 34, and I know that FG is equal to 25. Now, what I like the most about the segment addition postulate is, let's see if this makes sense. I'm going to take these values and go up here and put in 34, 25. So if I do 34 plus 25, what do I get? Well, 34 plus 25 should be 59. So let's see, and I do. I get 59. So I know that this works, right? And my answer is correct. I can always check my work by substituting back in and checking to make sure that along this segment, the entire length is 59, which it is. Okay. Remember, this is a video. So if I'm going too fast, you can stop and pause it. You can rewind it and listen again, so on and so forth. Okay. So let's continue. And let's now try something like this. And if you want, you can kind of pause this and try this yourself. I'm going to walk through it using the same ideas before. So now we're given that JK is 4x plus 6 and LK is 7x plus 15. They're also giving us this information here that JL is 120. So again, I like to put my little bracket from here to here, here to here, and now this value is 120. So again, I'm going to use a segment addition. I know that JK plus KL has to be the same length as JL. So I'm going to write that down, right? JK plus KL equals JL. Now, what do I know? Well, JK is this expression right here, which is 4x plus 6. So I can substitute that in for JK, 4x plus 6. KL is represented by 7x plus 15, so 7x plus 15, okay? And then I have my equal sign, right? So bring down my equal sign, equals, which JL? Well, JL is 120. Okay, so actually here's my new equation. The new equation I need to solve now is 4x plus 6 plus 7x plus 15 equals 120. So let's just do what we did before. Line down the middle, combine some like terms. So I'm going to highlight them first. I have my 4x and my 7x. That gives me 11x. And then I have my 6 and my 15. So I have positive 6 plus 15. So 6 plus 15 is our 21. Okay, and then I'm going to bring down my equal sign. Equals 120. Okay, now I want to get x alone, right? I want to work to get this piece here alone. So in order to do that, I have to get rid of the positive 21. So I'm going to subtract by 21. Do the same thing on this side. Subtract 21. All right, so now let's evaluate. So I draw my line. Bring down my 11x. 21 positive and negative 21, they kind of cancel, right? I get 0. And then over here, I have 120 minus 21, which is 99. Okay, so bring this over. Right? I have to keep my equation balanced, and x is not by itself. So to get x by itself, divide both sides by 11. And now I have divide by 11, divide by 11, and x equals 9. All right, so now I have the value of x. I have to find jk and kl. So like we did before, we said, okay, well, jk is equal to 4x plus 6. Here's the value of x that I'm going to substitute in, 9. So wherever I see an x, I'm going to substitute in 9. So 4 times 9 plus 6. So 4 times 9 is 36. 36 plus 6, 42. Okay, so here jk equals 42. Make this a little bit smaller. Perfect. And then down here, we need KL, and KL is equal to 7x plus 15. So 7x plus 15, wherever I see x, I'm going to substitute in a 9. So we have 7 times 9 plus 15, right? So that's 63 plus 15 is going to be 78. So KL equals 78. I'm going to kind of shorten that up. So the values that we were looking for here were JK and KL. So we have our JK is 42, KL is 78. And again, it has to add to 120. So you can kind of say, all right, so 78 plus 42 is indeed 120. So I know we're good. Okay, so that's how we kind of use our segment addition to solve for segment length. Now let's kind of think about this up here. So what could we say about segment AB and segment CD? And the first thing you might be thinking, well, it's pretty obvious, right? They both have 1 inch. So we might say that both are 1 inch long. Essentially, they have the same measurement, right? They're both 1 inch long. Well, if they're both 1 inch long, what did you say if they're equal? If this is 1 inch and this is 1 inch, well, then they're equal. So that's something else we can say. We can say that AB equals CD. We're given a length of 1 inch. They're both 1 inch long. That means they're the same measurement. Therefore, they're equal. Okay. So when when numerical expressions have the same value, right? They both have the same value. They're both 1 inch. You say that they are equal. Okay, so we can fill in that blank there. Say that equal. Now, here's something similar, but it's a little different. If two segments have the same length, okay, so now we're saying something different. We're not talking about the actual measurement. We're just saying the length. Like if you were just kind of to compare with, say, like the length of how long like a shoestring was, right? You don't know the exact measurement or the exact value. We call it something different. We call those congruent. Now, when two things are equal, we use this equal sign, right? When two things are congruent, there's actually a different symbol. And let me see if I can, let's actually draw the symbol in. It's an equal sign, and on top of the equal sign, you do like this little squiggle. So I'm going to actually draw it in to show you. So congruence is that equal sign with like a little hat, and it's like a little symbol like that. So this means congruent. Just the equal sign means equal. Now take a look. If two things are congruent, it's like you have an exact copy. So down here, A, B, and C, D, you would tell me that they're the same length, right? A and C match up, B and D match up. So they would be congruent. You don't see any numerical values here. But what you do see is this little like tick mark through it. When you see a tick mark, it tells you that if this segment has one tick mark, any other segment that has one tick mark is automatically congruent, is automatically the same length. So what I can say is I'm going to write a little note here so that you have it. This little tick mark tells us or shows congruent. So I look at that little symbol and I say, okay, they're congruent. Well, what does that mean? If two things are congruent, they're like exact copies. All right, well, here's something that's interesting. If two things are equal, they're automatically congruent. Right, so off to the side, I'm going to say it here, and this is really important. If two segments, really if two parts are equal, they are also congruent. And that's going to be really important for us later on in geometry. But right now, I'm going to make that red. If two segments are equal, they are also congruent. All right, so let's write a congruence statement then. Right, we have A, B, and C, D. So let's say we have A, B with C, D. We said they're equal up there, right? Now down here, I want to write that they are congruent. So let's see how it's different. If two things are congruent, A, B, and C, D. Now, what are A, B, and C, D? Or actually, let's start with this. Let's start with your congruent symbol. It's an equal sign. And remember, you have to put the little hat on top. Like that. Reminds you of like an enye if you took Spanish. Now, since the equal sign has a hat on top, we actually have to identify A, B, and C, D. What are A, B, and C, D? Now, they have endpoints, and they have a measure. So that means that they're segments. We're going to put a little bar up here. So whenever you're dealing with congruence, you have to use the correct symbol notation, right? And that's why last unit we spent so much time with rays and segments and lines and those segment notations. It's important. So now here's like the full conclusion. The full conclusion is if AB is equal to CD up here, then down here we automatically know that AB is congruent to segment CD. And it also works vice versa. If two things are congruent, they're also equal. Crazy how it works. Okay, so that's this. So now let's try to compare segment lengths and see what we come up with. All right, using what we know up here. Are segments AC and BD congruent? Before we figure out if they're congruent, or to determine if they're congruent, I first have to see, are they equal? So really, what is AC equal to, and what is BD equal to? And that's what we did before. We found segment length. So AC, let's find the length of AC. we know to find the length of AC, I could do the absolute value, right, of the coordinate of A and the coordinate of C. Oh no. So the coordinate of A is -2. Okay. Now the coordinate of C is not there. Well, that's weird. Okay, so how do I figure this out? Well, all right, if this is 4 and this is 6, I went up by, the difference between 4 and 6 is 2. Looks like this is right in the middle. So that means in the middle of 2 is 1. So that means that this is right in the middle of here and here, and this is the difference of 2. If I just go up by 1, then this has to then be 5. Okay, so C actually has a value of 5. So now this was a little different because C doesn't have a value in terms of it's not identified, but I can find the value. Okay, and actually before you go any further, B doesn't have a number with it either. Let's apply the same thing. It's right in the middle. This is a difference of 2. So I go up by 1. So from 2 and I add 1, that would be 3. So let me make this 3 before we go any further. I can go back down here. So I have AC, which is -2. And now C is going to be, so I'm going to do -2, right? And I'm going to do -5. Okay, so now I can take the absolute value of, well, -2 minus 5 is the absolute value of -7. Okay, the absolute value of -7 is just 7. So AC equals 7. Okay, so now let's do something similar for, what is it, BD. I'm going to take this and I'm just going to kind of clone it and cheat a little bit and change this to BD. Erase what's in here and erase what's in here. Giving some time. Let's see what we get. Okay, so from B to D, so we have 3 minus 10. So the absolute value of 3 minus 10, which 3 minus 10 is a -7. The absolute value of -7 is just 7. Okay, so AC and BD, they're equal, right? So we can come up with that AC equals BD. So since they're equal, they're also congruent. Let's actually change this. Since AC equals BD, and in parentheses I'm going to put they both measure 7, then we know AC is congruent to BD. Now again, I have to kind of change this a little bit since we're talking about congruence for the last portion over here. I do have to be careful. I have to put the segment on top of AC, the segment on top of BD, and I also need to include that little squiggly on top of my equal sign, like that. So there it is. So the answer here is also, we put yes, but it should always answer the question. And there's our explanation. Okay, so that's how you compare segment lengths. Okay, so why don't you try this one by yourself? And it says, use the diagram below. Is AB congruent to DE? So why don't you find the length of AB, the length of DE, and then compare. If they're equal in length, then they are congruent. While you do that, you can kind of pause this. I'm going to do this right now. So from A to B, and I have to compare from D to E. So AB is equal to the absolute value of -2 minus, now same thing, this would be 3. Okay, so -2 minus 3 is the absolute value of -5. Absolute value of -5 is just 5. So AB equals 5. And then over here, you can do DE. So the absolute value of 10 minus 14. Okay, so the absolute value of 10 minus 14 is the absolute value of -4. Absolute value of -4, DE is equal to just 4. So are they congruent? Well, since AB is equal to DE, wait a second, they're not equal. One is 5 and one is 4. So to show that two things are not equal, you put a little slash through the equal sign. So since they're not equal, 5 doesn't equal 4, then they're not congruent. So the answer here is, are they congruent? And the answer is no, they are not. 5 doesn't equal 4, so if they're not equal, they're not congruent. Okay, so this is going to be the first part of this lesson. Tomorrow we're going to actually talk about the midpoint.